Hi, my name is Parth Sharma, and today we're going to be talking about the P-series, on what intervals does it converge, how to prove that, and how it's useful. So our general form of the P-series right here is the sum from n equals 1 to infinity of 1 over n to the p. And the reason this is difficult is because we have that p variable, and that could be in any number of things, and we have to figure out for which number is that convergent. So the first scenario I want to take is when p is less than 0. So when p is less than 0, and I'm just going to rewrite this sum a little bit, so infinite sum n equals 1 to infinity of n to the negative p. Let's write it like that. So when p is less than 0, we know it's negative, and since negative p would just be positive, we know that this will always diverge. So say if p was negative 1, this would just turn out to be an n to the 1, and that series would just look like 1 plus 2 plus 3 plus 4 plus 5. And for whatever negative, that series will just get greater and greater. So this will always diverge. And that's helpful to know later on when we don't have to take the negative case anymore. So we already know from when p is less than 0, our series will diverge. So that's good. Now we're going to move on to when p is greater than 0. So right here, I've graphed out what it looks like for this series, and then p in this scenario would be equal to 1. But no matter what p you choose, the graph will look very similar. If it was negative, it would look different, but as we just said, we don't have to take into the negative account. We don't have to take the negative into account. So this is what our summation looks like. If we want to do the integral test and figure out what graph and where it's convergent, we'll just have to replace n with x, right? So 1 over x to the p, and let's just say p is 1 in this scenario, so 1 over x, that's our inverse curve. It'll look something like this. And so in this scenario, it is a graph. It does reflect kind of on our summation, but it's not helpful. And the reason it's not helpful is because it's actually less than our infinite sum. And if we prove that 1 over x to the p was convergent right now, it wouldn't show anything. It would just be like, oh, okay, but we don't know anything about the greater one, the infinite series. When something less than you converges, you can't prove that you also converge. The only way you can prove that you converge is if something greater than you converges. So what we're going to do is we're going to do some manipulation. So right now, let me write what our relationship is right now. Well, from 1 to infinity of 1 over x to the p dx is actually less than our infinite series from n equals 1 to infinity of 1 over n to the p. So what can we do to find something greater? Well, we don't have to do much, actually. All we have to do is add 1. So if we add 1 to 1 over x, you change, so before 1 would be equal to 1, but now it is equal to 2. 2 would be equal to 1 half, but now it's equal to 1 half plus 1, so 3 halves. So our graph is now moved up 1, and it's now totally greater than our series. And it actually doesn't matter what value p is, as long as it's positive, adding 1 to that function will always make it greater. So now we can write the last part. Sum from 1 to infinity of 1 plus 1 over x of p dx. So we care about this last part. If we can prove this is convergent, then we can prove that this summation is convergent. This infinite summation is convergent. Now we can do even more here, because if we split this up into 1 plus 1 over x to the p, so like the integral from 1 to infinity of 1 dx plus the integral from 1 to infinity of 1 over x to the p dx, well, we already know what 1 would be. It's just a number, so it's just 1. And that's always convergent. So all we really care about is if this last part is convergent. 1 over x to the p dx is convergent, and then we just add 1, it's still convergent. So we've kind of gone back to our first scenario. We've just proven that we can actually take this. So if we do take the if we do take the integral of this relationship, and we prove it's convergent, then we've also proven that our infinite series is convergent. So that's exactly what we're going to do now, right below. So we have here our relationship integral from 1 to infinity of 1 over x to p dx. And now we need to do some algebra and some calculus to figure out, is this convergent, and for what intervals is this convergent? Well, first things first, let's write it as a limit. So let's make our improper integral into something proper. 1r. Let's actually change the form here as well as we did before, x and negative p dx. So to find the antiderivative, we can just use our power rule. So that would turn into limit as r approaches infinity of, so it's x to the negative p plus 1, because when you take it, you'd subtract 1. And then since this would always also come out here, we have to divide by that. So it would be divide by negative p plus 1 as well. And that's from 1 to r. Now there's a problem here. Say p was equal to 1, well, negative 1 plus 1 is 0. So we can't even take when p is equal to 1 here. Fortunately, that's our only exception to this integral. So all we have to do is do the same thing here, but for when p is equal to 1. So we figured out that this is only when p is not equal to 1. So now let's actually take it for when p is equal to 1. When p is equal to 1. Well, 1 over x to the p will just become 1 over x dx. And we already know how to take the integral of 1 over x dx. So that'll just be limit as r approaches infinity of ln x from r to 1. Alright, perfect. So we have our antiderivatives. Now all we have to do is solve out. So let's do the bigger one first. This will turn into limit as r approaches infinity of r to the negative p plus 1 over negative p plus 1 minus, well, that's just 1 to the negative p plus 1, so just 1 over negative p plus 1. So we have this entire limit. We actually don't have to solve everything out or do some rules and tests for everything. All we have to do is figure out for r is negative p plus 1, because 1 over negative p plus 1, that's just a number. Negative p plus 1, that's just a number again. What we care about is this infinity. So as this reaches infinity, when will this be just a number as well? If this is just a number, then we'll be fine. This whole thing will be convergent. But if this r to the negative p plus 1 is not just a number, it's just infinity, then this whole thing will also be divergent. So now we can move down a little bit and just simplify what we're looking at. We're just going to be looking at limit as r approaches infinity of r to the negative p plus 1. Well, infinity to an exponent. How do we know when infinity to an exponent is convergent or divergent? Well, if we have something that's 1 over infinity, that's convergent. That'll always go to 0. So what we need to figure out is when this exponent is negative, because when it's negative, then we'll have that 1 over r, which is just 1 over infinity relationship. So finally, we've come here to negative p plus 1 has to be less than 0. If it's less than 0, we'll find the terms for when this is convergent. So if we do the algebra, we'll just figure out that p has to be greater than 1. Similarly, we can just flip this around. So when negative p plus 1 is greater than 0, this is divergent. So if we did negative p plus 1 is greater than 0, and we did the algebra, we'd figure out, so when p is less than 1, it's divergent. So there we go. We have a scenario, so when it's convergent, we have a scenario for when it's divergent. Now all we have to do is figure out for when p is equal to 1, our only exception. Well, this will just turn into limit as r approaches infinity of ln r minus ln 1. So again, as before, all we care about is this r infinity, and ln infinity, there's no scenario where that will not be infinity. This will always be infinity, this will always diverge. So when p is equal to 1, it's divergent. And so combining all the things that we've done, when it's less than 0, it's divergent. When it's less than 1, it's divergent. When it's 1, it's divergent. So for when anything is less than 1, when p is less than 1, it's always divergent. Only when p is greater than 1 is it convergent. And so that's the rule that we care about now. And how can we use this? Well, we can use this multiple ways. Say you just had this equation, 1 over, or say you had the sum of, let's just say 1 over n to the 2, n squared. Well, 2 is greater than 1, that's convergent. So let's do a little bit of that simple practice. So right here, we have our list of numbers here, and we see that the function is just 1 over n cubed. Well, 3 is greater than 1, so this is convergent. Right here we have 1 over root n. Well, root n is just n to the 1/2. 1/2 is less than 1, so that's divergent. Right here, n to the 5th, that's convergent. 5 is greater than 1. 1 over n, well, this is when n is equal to, when p is equal to 1. So we already proved that this is also divergent. So these are kind of the simpler examples. We can do a little more complicated ones as well. Let's take this example 1. The infinite sum from n equals 1 to infinity of n over n squared minus cos squared n. So let's write that out right here. Sum from n equals 1 to infinity of n squared over, actually wait a second, n minus n squared over n squared minus cos squared n. So this is just n. On the bottom we will have n squared minus cos squared n. So what we can do with our power series is use it in direct comparisons. So if we find that there's a power series that is greater than this and that converges, well, if something greater than u converges, you will converge. If we find a power series that is less than this and diverges, well, if something's less than u and diverges, you also diverge. So that's basically our direct comparison. So in this example, we can just say, let's just make it like this. Take all the clutter away. We can say that this fraction cos squared n. Well, cos squared n, the greatest this will ever be is 1, because cos of anything, the greatest that'll ever be is 1, and squaring that is 1. The rest is just decimals, and decimal squares, less than decimals. So this cos squared n will never get greater. It'll never become greater than 1. But this n squared, that'll really blow up. So we can just say that it's actually less than n over n squared. The reason it's less than is because you're still subtracting n squared. So say this was 1 over 1 minus 1, or no, sorry, we'd have to choose like pi or something. So we'd still be subtracting, we'd still be subtracting 1 or negative 1 or adding 1 to all of this. So it would still be less than what we have here, which is n over n squared, because the denominator here is actually less than n squared. So we now have this relationship is less than this, but we also know this is less, but this is actually equal to, this is equal to 1 over n. And we just proved that the infinite summation of n equals 1 to infinity of 1 over n is diverges by the p-series. So because something less than this diverges, which is 1 over n, this will also diverge. So that's just an example of how you can use the p-series as a direct comparison. And you can do it to multiple different things, as long as you maintain this relationship that 1 over n is less than this and diverges. If 1 over n was greater than n over n squared minus co squared n, you can't say anything, because it diverges, and if something greater than you diverges, you don't know if you diverge or not. So you have to maintain the direct comparison rules, but you can use the power series to compare to. So keep that in mind as you're doing your summations. That's basically it for everything on the power series. Hopefully this proof you can keep in mind and it'll help you out a little bit. And then also using it in different scenarios, p-series is very useful because the rule is so simple as if p is greater than 1, it converges. If p is less than 1, it diverges. Thank you.